at precisely 15.15 UTC, a really critical piece of orbital infrastructure is going to just completely power down its public radio relays.
Yeah, completely dark.
Right, because astronauts are stepping outside for a spacewalk. And, if you have the right $30 handheld radio pointed at the sky, you can literally listen to the exact moment that node on the grid just drops off.
It is, it's a really striking reminder of how fragile our communication networks actually are. I mean, we completely take for granted that our messages will just, route seamlessly through cell towers and undersea cables.
Well, totally. And satellites?
Right, but the moment you strip away those servers and the fiber optics, most people would have zero idea how to actually move data from point A to point B.
Which is exactly why this particular deep dive is so vital. I mean, Ranger Bob, if you spent 35 years in the IT world like our listener today, you are used to having, absolute control over your network architecture.
Oh, absolutely.
Packet routing, subnets, all those data pipelines. But what happens when you decide to build that exact same network out of thin air?
Yeah.
Completely independent of any telecom company.
Well, that's when you enter the realm of amateur radio.
Yeah.
And as a longtime operator, or an Elmer, as we call mentors in this hobby, I see a lot of IT professionals make this leap.
Yeah, I bet.
And they bring this incredible understanding of digital logic, but then they suddenly have to confront the physical, sometimes chaotic reality of radio frequency physics.
Right, like hardware constraints and just the established etiquette of the airwaves.
Exactly.
So we have a phenomenal mission today. We are pulling from a really dense stack of manuals, quick start guides, and technical schematics to bridge this gap between old school radio discipline and modern decentralized networking.
It's a huge leap.
It is. We are going to figure out how to avoid frying a basic Radtel RT900, how to bounce an analog signal off the International Space Station, how to generate physical telemetry with an Allego Uno R3 kit, and then finally, how to deploy a fully autonomous off-grid LoRa mesh network using MeshCore.
Like I said, it's a steep curve, moving from just, grasping the raw hardware in your hand to launching a self-healing digital mesh.
Okay, let's unpack this, starting with the absolute physical fundamentals, because before we can talk about cryptographic routing protocols, we really have to talk about voltage.
Yes, voltage is everything.
Because our sources are incredibly specific about the Radtel RT900 handheld radio and basically how not to destroy it on day one.
Right. So in hardware circles, we talk about the magic smoke.
The magic smoke, I love that term.
It's very real. Components operate using microscopic pathways, right? And if you introduce improper voltage, you literally vaporize those pathways. The component releases a little puff of smoke and, well, the device is permanently dead. And with the RT900, the primary threat vector for this is the side port.
Right, because the radio comes with this standard desktop charging cradle, which manages the battery voltage perfectly.
Yeah.
But then there's this port on the side of the chassis itself. And, I mean, for someone used to USB peripherals, it looks like a perfectly logical place to plug in a power cable.
Do not do that. Doing so will be catastrophic.
Wow, really?
Yes. That side port is engineered exclusively for data transfer and programming. It uses a specialized cable containing a UART interface chip.
Okay, so it's not for power at all.
Not at all. The pins inside that port connect directly to the radio's delicate internal logic board. They completely bypass the power management circuit.
So shoving 5 volts of high amperage charging current into that data port doesn't charge the battery, just blasts raw power straight into the CPU.
Exactly. Magic smoke released.
Okay, duly noted. Use the cradle.
Always. But the power threats don't stop at the battery, unfortunately. You also have to understand the radio's RF architecture, specifically the dual antenna ports on the top of the unit.
Right, it's got 2 ports.
Yes. The left port is your primary transceiver port that's designed for a standard VHF and UHF antenna.
Like the HYS TC286 dual-band whip antenna from the sources, the one tuned for the 144 megahertz and 430 megahertz bands.
That's the exact one. Now, the right port, or the middle port, depending on how you're holding it, is exclusively for wideband receiving. So that's for pulling in shortwave, medium wave, and long wave broadcast.
I think I see where this is going. It's kind of like a highway system. The left port is your two-way interstate for heavy traffic, transmitting and receiving. But the right port is like a scenic one-way dirt road just for listening to shortwave.
That's a great way to put it.
So if you accidentally hit the push-to-talk button while you're configured to that right port, you're transmitting a ton of power into a scenic dirt road that is only designed to listen.
Exactly. And this is where we run into a concept called impedance matching. Radio frequency is essentially alternating current. The left port and its corresponding antenna are matched at an impedance of 50 ohms. So when the final amplifier pushes out, say, 5 watts of power, that energy flows smoothly up the antenna and radiates out into the air.
Like a fast car on an open interstate.
Right. But that receive-only port on the right has a completely different impedance profile. If you force 5 watts into that port, the power hits an electrical bottleneck. It can't radiate outward.
So where does it go?
It reflects backward. It travels back down into the radio and slams into the final amplifier transistors as raw heat.
Yikes.
We call that a high standing wave ratio, or SWR. In the span of few milliseconds, that reflected thermal energy will physically melt the transistor.
Milliseconds.
Yes. The radio will power on, it will still receive, but it will never transmit another signal.
Wow. It's like the hardware equivalent of a catastrophic broadcast storm in an IT network. If you plug a 10 gigabit switch into a legacy 10 megabit hub, the traffic bottlenecks instantly, buffers overflow, and the hardware just crashes.
That is a highly accurate way to frame it. The traffic is raw RF wattage, and the crash is physical damage.
Okay, so assuming you have the correct antenna connected safely to the left 50 ohm port, you're finally ready to transmit. But this brings us to the actual etiquette, the operational rules of the airwaves.
Right, because unlike an isolated local area network in your server room, the RF spectrum is a shared public medium.
Which is why the sources really emphasize the national simplex calling frequencies. In North America, on the 2-meter VHF band, that's 146.520 megahertz, and on the 70-centimeter UHF band, it's 446,000 megahertz.
Exactly. Those frequencies serve as universal rendezvous points. Operators actively monitor them specifically to initiate contact with anyone in range.
But there's a strict protocol, right? You do not just hang out there. You don't strike up a 30-minute conversation about your weekend on the calling frequency.
Definitely not. The calling frequency is essentially a dispatch channel. You broadcast your call sign, someone responds, and then you immediately execute a QSY. Yes, it's the standardized Q code for changing frequency. You agree to jump to an unoccupied simplex channel, say 146.550, to actually have your conversation.
Oh, I see. So that clears the dispatch channel so other operators can make their initial connections.
Precisely. This raises an important question regarding how we actually utilize these VHF and UHF bands beyond just talking to the person down the street.
Oh, this is my favorite part. Because instead of just hitting a local water tower repeater, we can scale this up dramatically.
Yeah.
We can bypass terrestrial repeaters completely and target the International Space Station.
Yes. Orbiting at 17,500 miles per hour, 250 miles above our heads.
That is just wild. And the documentation on this is fascinating. The ISS houses a crossband repeater.
It does, which makes perfect sense from an engineering standpoint. If the ISS used the exact same frequency band to listen and speak simultaneously, its own massive output transmission would instantly deafen its highly sensitive receiving antennas.
Right, it would just scream into its own ear.
Exactly. So to solve that, it listens on one band and transmits on another. To access the ISS repeater, you configure your RadTel to transmit. That's the uplink on a VHF frequency of 145.990 megahertz.
Okay, 145.990.
But there's a secondary lock on that door. You must transmit a continuous tone-coded squelch system tone.
Oh, a PL tone.
Yes, commonly called a PL tone of 67.0 hertz.
So that 67.0 hertz tone is like this continuous subaudible hum that broadcasts underneath my voice. It acts kind of like a VLAN tag on an Ethernet packet.
That's a good analogy.
Because the repeater in space is constantly bombarded by terrestrial static and random RF noise, but it ignores all of it until it detects that specific 67.0 hertz tag. Once it hears the tag, it opens the squelch and accepts the payload.
Spot on. And once it accepts your uplink, it simultaneously rebroadcasts your voice on the downlink frequency of 437.800 megahertz in the UHF band.
Okay, so I just listened on 437.80.
Well, no, tuning to that exact downlink frequency isn't enough, simply due to the staggering velocity of the space station.
Wait, why is the frequency drift?
Because of the Doppler shift.
Ooh. Like an ambulance.
Exactly.
We usually think of Doppler with sound waves. An ambulance siren compressing and sounding higher pitched as it races towards you, and then stretching and dropping in pitch as it speeds away. The same exact physics apply to the electromagnetic radio waves coming from the ISS.
They absolutely do. And the frequency shift is profound. It often drifts plus or minus 10 kilohertz during a single pass.
Wow.
Yeah. As the ISS crests the horizon and hurtles toward you, the RF waves compress. The station is transmitting at 437.800 megahertz, but your radio will perceive the signal as arriving at 437.810 megahertz.
So I have to actively manage my hardware in real time. I can't just set the dial and walk away to make coffee.
No, you cannot. You have to program a sequence of memory channels stepping down in 5 kilohertz increments. You start listening high as it approaches, switch to the true sender frequency as it passes directly overhead, and then drop down to 437.790 as it recedes over the opposite horizon.
That requires some intense manual coordination.
It does. And surprisingly, the antenna strategy for this is really counterintuitive to most beginners. High-gain directional antennas like a Yagi are excellent for terrestrial range because they squash the radiation pattern down flat against the horizon.
But the ISS isn't on the horizon for very long. I mean, the best signal is when it's directly above you, so a flat radiation pattern is actually a liability here.
Exactly.
So a simple omnidirectional 14-wave whip antenna, the kind that naturally radiates in a big round donut shape up into the sky, actually outperforms a complex directional array during an overhead pass.
It really does. Simplicity often wins in RF physics. But remember that critical scheduling detail we discussed at the very start of the deep dive.
Oh, right, June 29th, 2026.
Yes. At 15.15 UTC, the astronauts will power down all amateur radio equipment to ensure no stray RF energy interferes with their spacewalk. The repeater will be completely dead air.
Also worth noting, there's no slow scan TV currently scheduled to be broadcast from the ISS either.
Right, the last one was Series 32 back in May.
Okay, so we've mastered receiving data from space and bouncing voice signals across the analog spectrum. But to truly build an off-grid network, we need to generate our own digital data.
Which brings us to telemetry.
Yes, this is where Ranger Bob's IT background takes center stage, specifically regarding the Allego Uno R3 Superstarter Kit.
Moving from analog voice transmission to digital telemetry is really the bridge into modern mesh networking. The Allego kit is built around an Arduino microcontroller.
Right, it comes with the breadboards, motors, LEDs, and those crucial and environmental sensors.
Exactly. It allows you to write code that interacts directly with the physical world.
Which is so cool because in traditional IT, data pipelines usually start with, like a server log or user input. But here, the data pipeline starts with the actual ambient temperature of a room. We just connect a physical temperature sensor to the GPIO, the general purpose input-output pins on the microcontroller.
Right. And the sensor converts that thermal energy into a raw electrical voltage. The microcontroller then pulls that GPIO pin, reading the voltage fluctuations.
It's essentially the hardware version of an SNMP pole checking a router's status. But to process that raw voltage, we need software. Now, I know Python is basically the dominant language in network automation right now, but our sources are clear that the Arduino IDE relies on a framework built on C and C++.
There is a very specific reason for that. Python is a high-level interpreted language. It completely abstracts away memory management.
Yep.
But C++A, particularly in the Arduino ecosystem, is much closer to the bare metal. It allows for strict timing control down to the microsecond.
Which you need to read those delicate electrical pulses without releasing the magic smoke.
Precisely. Timing is everything with physical hardware.
Okay, so we write our C++ code, we pull the GPIO pin, and now we have live temperature data sitting in our microcontroller's memory. The immediate IT impulse here is to scale this up. But I want to build a mesh network right now with this kit. I want to take this Arduino Uno, wire it a LoRa module like an RFM95, and just blast this telemetry across a citywide mesh network.
I admire the ambition, really. But that architecture will fail. Wait, why? Because the Arduino Uno is powered by an 8-bit 18-mega 328p chip. It has exactly 2 kilobytes of SRAM.
2 kilobytes of operating memory. That is staggeringly small.
It is. It's like a trusty bicycle, great for learning the neighborhood, reading a temperature sensor, blinking an LED. But modern mesh networking firmware like Meshtastic or MeshCore requires the device to maintain complex dynamic routing tables.
No, right.
It has to store cryptographic public keys for secure messaging, manage packet queues, handle state arrays for dozens of connected nodes simultaneously.
Okay, I see. It's the equivalent of trying to load a global BGP routing table onto a $20 home internet router. The memory buffers will instantly max out, the CPU will choke, and the device will lock up.
Exactly. The 8-bit architecture simply cannot handle the computational overhead of encrypted packet routing. To run a true cross-country mesh network, you need the sports car. You need a massive upgrade in silicon.
A 32-bit architecture.
Yes, with hundreds of kilobytes of SRAM. In the maker world, that upgrade is the ESP32 chip.
Which brings us to the ultimate frontier of our deep dive, The ESP32 is this low-cost, low-power system-on-chip that integrates built-in Wi-Fi and Bluetooth alongside the processing power needed to actually juggle that cryptography. And when you pair an ESP32 with a LoRa radio like the Wio Tracker L1 Pro from the sources, you unlock MeshCore.
MeshCore represents a total paradigm shift. It is a completely off-grid, secure communications application.
We should probably define LoRa for a second. It stands for long range. It utilizes a modulation technique called chirp spread spectrum. So instead of broadcasting on one tiny fragile frequency, it sweeps a chirp across a wider bandwidth.
And that sweeping chirp is incredibly resilient to interference. Even if the transmission power is incredibly low, mere milliwatts, and the signal actually falls below the ambient RF noise floor, the receiving LoRa chip can mathematically reconstruct the chirp.
That's amazing. So it essentially trades bandwidth for distance. The data rate is agonizingly slow-like, comparable to an old 14.4K dial-up modem, but the range is measured in miles, completely independent of cellular towers, ISP fiber lines, or Starlink.
Yes. To interface with this, you install the MeshCore app on your smartphone. The phone handles the user interface, pairing to the ESP32 node via Bluetooth.
And according to Liam Cottle's November 2025 Quick Start Guide, if you were using a screenless, headless node, the default pairing PIN is just 123456.
That's right. Once paired, the phone acts as your terminal, but the ESP32 node handles Layer 1 and Layer 2 of the OSI model, the physical radio transmission, and the data linking. But we have to remember, because we are still broadcasting RF into the public airwaves, regulatory compliance is baked into the software.
Right. The rules still apply.
Very much so. Every country allocates specific license-free industrial, scientific, and medical bands. The MeshCore app simplifies this through community presets.
So if you are operating in New Zealand, for instance, you simply select the preset for 917.375 MHz with a 250.0 kHz bandwidth.
Exactly. The app pushes those parameters to the ESP32, ensuring your hardware remains legally compliant.
So with the node compliant and broadcasting, we tackle identity. Because in a traditional centralized app, you create a username on a company's server. But MeshCore is completely decentralized, so identity is handled purely through cryptography. You are identified by your public identity key.
Yes. And you can exchange these keys in person by scanning QR codes, which establishes a secure, encrypted tunnel between two nodes. But if you are trying to discover new nodes in the wild, you utilize the advert feature.
Right. An advert is an unencrypted plain text packet containing your node name and your public key.
Oh.
It's the digital equivalent of shouting, "I am here, and here is how to securely route packets to me."
Exactly.
And the software gives you two ways to broadcast this: zero hop or flood routed.
Zero hop limits the broadcast to line of sight. Your node transmits the advert, and only the physical radios within direct listening range will receive it. They will not pass it along.
Here's where it gets really interesting. Flood-routed messages. Because in traditional IT, packet flooding is usually a bad thing. It causes network loops and crashes. But in MeshCore, it is the foundational routing protocol.
If we connect this to the bigger picture, imagine deploying a solar-powered ESP32 node in a waterproof box at the top of a local mountain. That node acts as a passive repeater.
Oh, wow. Okay, so when you send a flood-routed message from the valley floor, your node broadcasts it. The mountain repeater receives it, checks its routing table to ensure it hasn't seen this specific packet ID before, and then rebroadcasts it with maximum power across the entire region.
Yes. And any other nodes that hear it will repeat the process, decrementing a time-to-live counter in the packet header until the message reaches its intended recipient.
It literally turns a sprawling geographical area into a decentralized self-healing subnet. If a storm takes down a telecom tower, it doesn't matter. The MeshCore routing algorithm dynamically finds a new path through surviving solar repeaters. You have effectively built your own ISP out of $30 microcontrollers and a few watts of solar power.
You have reclaimed ownership of the infrastructure.
Ranger Bob, what an incredible technological arc we've covered today. We started at the bare metal, learning how impedance mismatches and reflected SWR power will instantly let the magic smoke out of your RadTel RT900.
And then we moved to the operational discipline of calling frequencies, learning how to effectively manage the shared spectrum through standard QSY protocols.
We looked up into orbit, breaking down the mechanics of the ISS crossband repeater, from the necessity of that 67.0 Hz sub-audible squelch tone to actively chasing the Doppler shift in 5 kHz increments as the station screams overhead.
Then we transitioned into data creation with the Allego Uno R3, exploring how C++ gives us the microsecond timing required to pull physical GPIO sensors, while recognizing that an 8-bit architecture simply lacks the SRAM to handle cryptographic mesh routing.
And finally, we scaled up to the 32-bit ESP32, exploring how LoRa's chirp spread spectrum and MeshCore's flood routing protocols allow you to build an autonomous, encrypted network that survives when the traditional grid goes dark.
Which brings me to a final thought for you to ponder, Ranger Bob.
Yeah.
Early on, our sources mention the ICOM IC705.
Oh yeah, a brilliant, highly advanced piece of amateur radio equipment.
It is. It features D-Star, a digital voice protocol that allows you to link your local radio transmission to internet gateways, essentially talking to operators on the other side of the planet.
It's an incredible feature right up until the fiber optic lines get cut.
Precisely. If the global internet backbone fails, that high-end digital capability vanishes, and the IC705 is reduced to a standard local transceiver. So as traditional telecom infrastructure becomes simultaneously more sophisticated and more fragile, we must ask ourselves a critical question.
What's that?
Will the future of communications be defined by operators boasting the most expensive transceivers and the highest wattage? Or will it be defined by the quiet engineers who have meticulously built a resilient, low-power, decentralized, self-healing digital mesh right in their own backyards?
Man, that is the ultimate architectural challenge. Ranger Bob, we hope this deep dive has armed you with the theoretical and physical knowledge to tackle this new frontier. Keep writing code, keep analyzing the spectrum, and most importantly, keep building that grid. We'll catch you on the next one.